Okay, 3:05, recording started, and we can start our session as well. Okay, so before we get into a new topic today, once again we go through a little recap, all right? So on Monday's lecture, you have been exposed to a few terminologies, which I would like you to revise once again, right? So first would be, what is branch, all right? So a branch is essentially a path through an element, all right? So as you can see here, from 2 to 1, this will be better. From 2 to 1, in other words, from this path across this current source, we can say that this is a branch. Likewise, from this end to this end, across the resistor, is also a branch. Likewise, here to here, a branch. 1 to 3, a branch. 3 to 2, another branch. Okay? So aside from branch, another thing that you need to take note of is what is a node. Okay? A node is essentially a point at which two or more elements have a common connection. Alright? So for instance here, how many nodes do we have? 1, 2, and 3. Nodes 1, 2, and 3, right? So you can see that these are the points in which two elements are having a common connection, right? So this resistor here has a common connection with this resistor here. So this is a node, this is also a node, right? And likewise, this has a common connection with this guy here via this node here, which is node 3. Okay? Another thing that I would like you to take note of is that in certain questions, you'll notice that your connection is actually expanded in this way, right? As you can see here. From this to this. One second. So from this image to this image here, okay? So you notice that essentially what we are doing is we are actually breaking this node into a path, right? However, you must not get confused. This is just a path and not a branch. This is a path and not a branch, okay? It's essentially just another node, okay? So if you recall your lab activity this week, remember in one of your tasks, I would say the first task, you're required to set up your power supply with 2 channels, right? So in channel 1, you set it with 10 volts, if I'm not mistaken, and channel 2 with 6 volts, right? So when you transition over to task 2, in which you are required to do the measurements, notice that some of you actually did something like this, right? Remember, you have your probe, one of your probe placed at the ground, the common, I would say, the common probe. You had your common probe from the multimeter placed at the ground, right? And you have your rate probe, right, from the multimeter placed over here. Okay? Oops. So when you did this, you notice that the measurement that you get is essentially 0. So why is it so? This is exactly because of this scenario here, right? Although it looks like a path, it is essentially just a node. And this node is apparently connected to ground. And as a result, you're getting 0 on your multimeter reading. 0 volts on your multimeter reading, okay? So don't get confused when we are breaking apart a node into a path, okay? Right? So moving on next. There's nothing, yep. So after the concept of nodes and branches, you need to take note of what is a loop, okay? So a loop is essentially a closed path, right? So as you can see over here, the one in blue is a loop, okay? Yep. Okay. It travels from this end here, for instance, all the way around the circuit itself. This is one loop. Notice that this is also a loop, okay, because this is a closed path. This is also another loop because it is also a closed path. So this circuit gives us a total of 3 loops, okay? So moving on next, after you understand really well about nodes, loops, as well as branches, the next thing to identify is what are series and what are parallel circuits, right? So parallel circuits essentially means that any branches that are connected between the same two nodes are in parallel. Yep. So in this diagram here, and as well as your lecture notes, you notice that it states that R1, R2, and R3 are in parallel. Yep, that's true. However, one thing that you can note as well is that both R4 and R5 are in parallel with R1, R2, and R3 as well. Okay, because they share the same node here. Okay. All right. So take note, like I mentioned here, both, right? Both R4 and R5 are in parallel, right? Independently, however, if you are just considering R4, you cannot say that it is in parallel with R1, R2, and R3. Likewise, the same goes with R5 as well. Okay? So this is the idea behind parallel circuits. And one more thing to note about parallel circuits is that voltage across parallel paths are the same. Okay? So what it means here, let's say, let's say I have a voltage across R1, okay, I call it V, and I have a voltage across R2. The property is that V1 and V2, sorry. The property that I have is V1 equals to V2. And likewise, you can say that the voltage across here is also the same, and voltage across R4 and both R5 is the same as well, right? This is one property that is very useful when it comes to solving circuit problems, okay? And after understanding parallel circuits, the next one will be a series circuit. So a path in a series connection of components, a path is a series connection of components if all intermediate nodes in the path have no other connection, okay? So we look at this, look at R2 and R3, they are connected by node 3 here, right? So is this a series connection? It is, because there are no other connection, no open connections at the intermediate node, which is N3. Okay? However, if you look at R1 and R2, are they in series? No, because node 2 here has an extra connection here, which connects to the current source. Okay, clear? Right? So after identifying parallel and series circuit, you're also introduced to this first tool, which is, I would say, the second tool, which helps you to solve circuit problems, which is called the Kirchhoff's current law. So Kirchhoff's current law states that the sum of currents entering a node is essentially 0. So this is fairly straightforward here. So if you take a sum of IA, IB, ID, and IC, of course, you need to take into account of the direction as well, you'll have a total sum of 0. Okay? So by applying Kirchhoff's current law into the case of multiple resistors in parallel, you notice that you can actually find the equivalent resistance, which is given by the reciprocal of the summation of the reciprocal of all the resistance. Okay, so this is a fairly complex formula, as you can see here, right? However, I would like you to take note that this equivalent resistance is only applicable when you have resistors that are in parallel. Okay. So if you go one step further, we also can have this current divider rule, or what we have here called current division, and the equivalence, and say you have a source current of I, okay, you can actually find the independent current across each resistor as according to this relationship here, right? You have the R equivalent, which is from the previous slide, okay, this one is actually equivalent to this one, okay? And you divide it by the resistor of interest, and you multiply it by your current source, okay? And this gives you the current across the resistor at each path or each branch, okay? Right, so this is a very short wrap up on Monday's lecture, I think. Yep, okay. Right, so after this, today you'll be looking into the third tool, which helps you to solve circuit problems, which would be Kirchhoff's voltage law. Okay, so it's kind of similar to Kirchhoff's current law, aside from the fact that it states the sum of voltages around any loop is actually equals to 0. Okay, So, so once again, I emphasize that every electrical component in your circuit has 3 parameters. You have the voltage, you have your current, you also have your resistance, right? So if you take into consideration of all the components in the circuit and give them a voltage value, say this is, I'll just call this V1 for instance, yeah? V1, V2, V3, V4, yeah? And maybe V5, okay? Yeah? You notice that when you go around the loop, the summation of all these voltages is essentially equals to 0, okay? The concept here is fairly easy, right? Kirchhoff's current law mentions that the total sum of currents entering a node is 0, okay? Voltage law, the total sum of voltages around any loop is 0, okay? Everything is just essentially equals to 0, right? This is basically a principle of conservation, yeah? Right? So, I will talk about it later, talk a bit more on this when I do a summary later. But now let's do a quick example on how you are going to apply Kirchhoff's voltage law when it comes to solving circuit problems, okay? So say today you have a circuit that's shown in this figure here. So how are you going to use, or how are you going to apply Kirchhoff's voltage law? So if you go back to the definition a bit, it says that the sum of voltages across any loop, okay? So the key is here. So if you are to apply Kirchhoff's voltage law, you need loops, right? So now, let's draw a loop here. Maybe this is easier this way. Okay, let's draw a loop. Okay, this is the loop, right? Okay. So once you draw a loop, what you need to do is travel along this loop here, okay? And sum up all the voltages that you can see along the components, okay? Right. So let's start with this. So another key point to take note here is that when you travel along the loop and gets across each of the voltages, yeah. So how are you going to assign a polarity to them, right? So it's fairly simple. What you can see from this statement is entering an assumed positive node means that the voltage drop is taken as positive. Vice versa, if you enter an assumed negative node, you will take a negative voltage, right? So let's start from this starting point here. Okay, let's start from here. Let's start from here. Okay, starting from here. So the first node, the first voltage that I encounter is V4, right? Notice the polarity here, negative V4. Okay, so I have negative V4 written over here. Okay, I travel along. Okay, the next one I encounter is V1. Okay, the polarity here is positive, so I take this voltage as positive, plus V1, correct? Then I travel along again, hitting V2. Once again, we have a positive terminal here, so you have V2. And going to the last one, you have negative, you have V3 here, but you enter the negative terminal first, so you have negative V3, okay? So you have basically you have the left-hand side of the left-hand side of your equation here. Then going back once more to the definition here, sum of voltages around any loop is 0, right? So you just need to equate them as 0. Okay? As simple as that. Okay, moving from here, negative first, so negative V4, positive first, so positive V1, positive once more, positive V2, negative, so negative V3, and we have a equals to 0. Okay? Very straightforward. Right? So now, I'll go into one of the actual questions that you might actually see in your exams, okay? So now it says, if I have a resistor, I assume a direction of current flow and define the voltage polarity. This is kind of similar to what I mentioned last week. Remember, I actually listed to you 3 different steps in solving electrical circuits, right? So now, once again, I'd like to point out that it is okay to assume any current direction, okay? So in this slide here, you notice that the current direction is assumed in this direction here. It is a clockwise direction. Of course, you can go the other way around. You will still be getting the same answer as well, right? So for starters, I'll just repeat the process of applying KVL to solve this circuit, right? Right, so start from here. So I'll create a loop, okay? So my loop here can follow, oh, right, so sorry. So before we go into creating the loop, remember after you assume your current direction, the next step is to determine the polarity of your components, okay? Based upon the current direction that you assume, right? Remember in that what I mentioned? When you're looking at a load, right, current must enter through its positive terminal. So we assign a positive here, okay? So I won't talk about V1 and V2 for now first, right? So this is the assumed current direction. So based on this assumption, when I hit a resistor, R1, I automatically assign plus here because a resistor absorbs energy, okay? So going on here, I hit R2, and since my current is going into R2 here, this must be the positive terminal, okay? So now, I can solve my problem, okay? So the first step, I determine that, okay, I'm going to use KVL and Ohm's law, right? So what do? KVL, draw a loop first. Okay, let's draw a loop. Okay. So from drawing a loop, what I can do, I can also label the voltage across the resistor here as V3 maybe. V3. Voltage across resistor 2 as V4. Okay? So going really slowly, what you can see, I'll travel from this starting point here, going up, negative V1, okay? Hitting this one, we have plus V3. It's a bit ugly. Yep. And going to here, we have plus V2. Hitting R2 here, we have plus V4. Okay? So by Kirchhoff's voltage law, this must be equals to 0. Okay? So can I further represent my equation here? Can I further expand it? Yes, because we have a resistor value here, R1. Okay, so what we can do here, we apply Ohm's law. Remember Ohm's law is V equals to IR, right? Okay. So I have negative V1. V3 here is essentially the current multiplied by I1. So we have I plus R1. Okay. V2 is still V2. No changes. When we hit V4 here, you have plus I times R2. Okay? So this is essentially the answer that you see over here. Right? Okay? So now this point here, the annotation here, it is also okay to assume clockwise or counterclockwise loops. Okay? So I'll demonstrate it here real quick that it is okay if your assumed loop is in the other direction. Okay? Right. Okay. So just redraw the circuit first. Okay, I put in the labels. This is V2, V1. This is V2. This is V3. Okay, this is V4. This is R2. This is R1. All right, so I will still assume my current direction here, which is I. Okay, so after assuming this current direction, I set my polarity. So this is a load, so it absorbs energy. So this must be positive terminal. Go around here. Positive here, negative here. Okay? So now, unlike what we have on the slide here, just now I have a clockwise loop, right? So now I have a counterclockwise loop. Okay? This is counterclockwise. Okay? So can I get back the same result? Okay, this might be my starting point now. This is my starting point. Okay, I hit the negative terminal first. So I have negative V2. Okay? Going up, I hit the negative terminal once again, negative V3, plus V1, and negative V4. Okay? Applying Ohm's law. Applying Ohm's law to R1 and R2. I have negative V2 minus I, right? R1 minus, plus V1. Okay. Then we have minus I R2. Okay, equals to 0. All right. So essentially, if you multiply both sides by negative 1, you just get back the same thing, isn't it? Negative V1 from this one here plus IR1 plus V2 plus IR2, you're still getting equals to 0. Right? So this means that it doesn't really matter whether your assumed loop is actually clockwise or counterclockwise. So my idea is that you can just set your mind on one direction, then just use it for the entire course. Okay? Right? Okay. So going on, we have the next example. Okay, for this one, so I'd like to take the opportunity to give some extra information on what I mentioned on last Friday's lecture. Right? On last Friday's lecture, I actually just introduced you to three steps, three sequential steps in which you can use to solve your every circuit problem, right? So after going through some tutorial sessions and receiving some feedbacks from the students, I think I've come up with a more improved version of these steps. Yeah. So I'll demonstrate. I'll just show you here. So I'll increase the steps from 3 to 5. So I call it 5 less error-prone steps for your circuit problems. Okay. So for starters, what I will encourage you is to always redraw your circuit. All right. And redraw them without any values and current flow. Okay, just ignore the values for the time being, as well as the current flow that is drawn on the question diagram itself. Okay, then you can do your own labels for each components V and I and R. Okay, label them. Okay. So after this, you can go on to the next step. You can assume a current direction, which is what you usually start off with. Assume current direction. And based on this assumption, remember this is very important. Based on your assumption, always based upon your current direction, set the polarity. Okay. So these are two notes that I was saying just now. So if your current should always leave the positive terminal of components which delivers electrical energy. Okay. If it is delivering, you must have your current must leave the positive terminal, right? So take note that I'm using the terms delivering and absorbing instead of source and loads, because when you go into AC circuits, you'll notice that some components can actually do both, right? Depending on how the current is actually flowing. So I think it's best if I leave the terminology as follows, so you can use it for both DC and AC circuits, right? So take note once again, current leaves the positive terminal of components that are delivering energy, and current enters the positive terminal of components that are absorbing energy. Okay? So once this is done, you can refer to your question once again and start to assign the values to your labels. Okay? Start assigning values to labels in your first step. Okay? So determine the formulas that you can use, determine the formulas, and happy solving. Okay? So once you're done, the fifth step is very important, okay? Check if your final answer is in the same direction and polarity as required by the question itself, okay? Make sure that the polarity is the same as illustrated in the figure, okay? And of course, don't forget SI prefixes and your SI units, okay? Okay, believe it or not, these SI units can actually cost half of your total marks. Yes, question? Oh, yeah. Yes, that's correct. It should be a positive, enters positive. Okay? A little correction here. Why can't I? Yep. This should be positive. Yep. Yep. Thanks for that. This must be positive. Oh my God. Positive. Not negative. Okay? Enters positive terminal or components that are absorbing energy. Okay? So in this case, if you're looking at a resistor, okay, the first point of contact with the current should be positive. Okay? Alright? Clear? Okay. So you'll use these 5 steps here in solving the problem we have just now. Okay? Yes? Energy, E. E for energy. Yep. This. All right, I'll use these 5 steps in solving this problem for you. In solving this problem together with you. Okay? So I'll draw this first. While you take notes. You take your time to take notes, fine. Okay. Okay, done? Right. So what have I done here on this document scanner here? I went through step 1, okay? I redraw my circuit, okay, without any values or any of the current assumptions here, okay? Everything is blank, okay? So I'll label my components. I call this guy VA, VB, okay? I have a VC here as well. I just call it VX, right? Then, yep, it's done. Okay? So step 1 is done. I have a bare bone circuit with my own labels. Okay? I'll try to solve this problem with only my diagram here. Okay? So step 2, assume any current direction. Okay, any is fine, like I mentioned just now. If it's the wrong direction, you just get a negative value and flip it over, right? So I call my current I. Remember, this is a series circuit, so the current flowing through this voltage source is the same as the current flowing through this voltage source, and it's the same as the current flowing through the resistor as well. Okay? Now I need to assign my polarity based on this current flow. Okay? So this voltage source here delivers energy, right? So current should leave the positive terminal. Okay? So this is leaving, current is leaving here, so this must be positive according to my assumption. Okay? Likewise, going down here, this is a load, this is a component which absorbs energy. So the first point of contact should be positive, negative here, right? Going down to VA, or this voltage source here, the first voltage source here. Okay, this is the component that delivers energy, so this must be my positive terminal, this must be my negative terminal. Okay, apparently this is easy because it coincides with the figure itself. Right? So now we can refer to the question and assign all the values that we have according and in accordance to our little diagram here. So my VA is equals to 5 volts, correct? Okay. VB is equals to 7 volts. Okay. Vx. So Vx is what we want to find, I think. Yep, Vx is what we want to find. I'll just change this to Ix as well. Okay. Vx is what? Ix is what? Of course, I forgot to label my R1 here. Okay, that's on me. So R1 must be equals to 100 ohms as well. Okay? So now today we will be using Ohm's law and what's it again? Kirchhoff's voltage law to to find these two values, Vx and Ix. So we can use Kirchhoff's voltage law first. Yep. Applying KVL. Okay, to apply KVL, of course, you need a loop. Let's have a clockwise loop today. I call it loop 1. Apply KVL around loop 1. Okay? So I'll start from VA here. So it's negative VA, negative VB, and what do we have? Plus Vx, right? Equals to 0. So I can plug in my values. VA is 5, VB 7, Vx 0. So Vx is essentially equals to 12 volts, right? Okay? Okay. Right. So now we are up to step 5. Check if the final answer is in the same direction of polarity. Okay. So now check Vx here. Check. Okay, my Vx here. The assumed Vx I have is plus here, minus here, and in the question, I have a plus here and a minus here as well. Okay. So my answer of Vx is definitely correct. Okay. So now the question is, what is Ix? Okay. Once you have Vx, recall once again, every component has its own Vi and R. Okay? So apparently Ix is equals to just Vx divided by R1, applying Ohm's law, right? Applying Ohm's law. Okay? So Ix is just equals to Vx divided by 100. So it gives us 0.12 and in engineering notation, 120 milliamperes. Okay? So these are the 5 steps. Of course, you'll notice that it takes a lot more time, but over time with practice, you'll notice that you'll get more and more familiar with all these questions, all the steps, then you're actually free to do any simplifications of your own, right? So these 5 steps are just a guideline here for all beginners. Okay? Right? So, moving on. Okay, done. Now, this is a more complex one. So I'll be doing a few skippings here. I won't be going through the 5 steps now due to time constraints. I'll just draw this here once more. We have a blob here. So a blob, essentially, you don't know what is it. It can be a resistor. It also can. It might be a load, or it might be a component that absorbs energy, or it might be a component that delivers energy. Okay, we're not sure. So call it a little blob here. Maybe I'll just represent it by a triangle. Maybe. Yep. Okay, this is VR2. This is 12 volts. This is plus minus 14 volts. Right, so I won't label what is here because look at the question. The question just wants us to find VR2 and Vx, right? VR2, Vx. Okay? So Vx is essentially the potential difference across terminals A and B, Vx. Okay? So to solve this question, we can actually do a little trick. Okay. Remember, to apply Kirchhoff's voltage law, you need to have a closed loop, right? So we are in luck because the Vx here allows us to create a closed loop here, right? So I can somehow close this path here. Okay? I can somehow close this path here. And I can do KVL in two loops, L1 and L2. Okay? So, do I need to assume my current direction? In more complex problems, I would say you need to assume a current direction. But in this example, we are given all just pure voltages, right? So, it's okay if no current directions are assumed for now. Okay? However, take note in your exams, questions won't be as simple as this. Okay? So, current direction must always be assumed beforehand. Okay? Now, let's say apply KVL around loop 1. Okay. Hitting here, I have 1 volt. This one, 36. Negative 36 volts. Hitting this one, plus VR2, right? Plus VR2 equals to 0. This is loop 1. Okay. So VR2 is equals to? Answer? What's the answer? Negative? Negative what? 35, yes. Negative 35 volts. Okay. So half of the question almost done.
Positive.
Correct. Okay. Right. So now, we apply KVL. Around loop 2. Okay. I'll be hitting negative VR2 plus 12 volts. Okay, here, and plus 14 volts again. Okay. Then I'll hit my Vx here equals to 0. Okay, KVL. I have my VR2, which is 35 volts plus 12 volts plus 14 volts plus Vx equals to 0. So Vx is equals to? Answer? What? Minus 9? Wait, something is wrong here. Oh yeah, here, I forgot the negative sign here. Yep. Okay, VR2 is 35. Okay, misinterpreted this. So it should be 9 volts, right? Correct? Okay, sorry for the little error. Okay. Then we are done with this question. All right? Right. All good here? All good? Right? Right. So next, when you have a voltage source in series, it's kind of similar to what you have last week when you have 2 current sources in parallel. You can just sum them up together. Similarly, when you have 2 voltage sources in series, you have your equivalent voltage, which is equals to VA plus VB. Okay, VC is equals to VA plus VC is equals to VA plus VB. Okay, straightforward here. Okay. Okay, so now, last week you applied KCL to resistors in parallel, multiple resistors in parallel, and it allows you to find the equivalent resistance in a circuit, right? So today, you can apply KVL to resistors in series and find the equivalent resistance. Okay, so how do you do? So look at this figure here. Okay, we have 2 resistors. Okay, 1 voltage source. You can apply KVL, right? You have label V here, V1 for the resistance 1's voltage. And the voltage for resistor 2 is labeled as V2. Okay, KVL, we have V equals to V1 V2, right? Just write one step before that. Skipping some steps here. So I have a loop here. I have negative V plus V1 plus V2 equals to 0. Oops. Okay. Therefore, if I move this over here, we have V equals to V1 plus V2. Okay. So applying Ohm's law, we have V equals to IR1 plus IR2, right? Remember, current in a series circuit is always the same across all components. You can factorize out your I, the current. You have V equals to I, R1 plus R2, okay? And if you represent this circuit, this big circuit here, into a simpler one, okay? This is essentially your equivalent resistance is essentially R1 plus R2, right? Okay? Right. So now resistors in series, example. So for this question, the first one, resistors in series, 39 kilo ohms, 15 kilo ohms. So to solve this problem, it's fairly easy. We can just refer to what we have a slide above here. Okay? If it is in series, we can do the first resistance plus the second resistance, right? So what's the answer here? R equivalent. So essentially what we are doing is, from here we want to have something like this. R equivalent, right? Yep. So R equivalent is equals to 39 plus 15, which is equals to 54 kilo ohms, right? Yep. So for the second example, for this A, for this B, we have a 10 kilo ohm, 56 kilo ohm, 82 kilo ohm circuit, right? So I want to find the equivalent resistance. I want to do something like this as well. But before that, so how can I crack this problem? I can crack it by this way. I simplify it first. Instead of having a series and a set of parallel resistors, what I can do, I want to have something like this first. 10 kilo ohms. Okay? I crack it down to a smaller R equivalent. I call it R equivalent 1. Okay? So R equivalent 1, this needs you to apply Kirchhoff's current law. Okay? Or you can use the equivalence resistor formula right away, which gives us something like this: 1 over 1 divided by 56 plus 1 divided by 82, right? Or likewise, you can say it's just 56 times 82 divided by 56 plus 82. So this gives us 33.3 kilo ohms, right? So now the problem simplifies from a combination of 3 resistors to a combination of 2 resistors. And now we can go further to just 1 resistor here, which is the final equivalent resistance that we want. Okay. So R equivalent is now simply 10 kilo ohms plus R equivalent 1 here, okay, which is 43.3 kilo ohms in total. Correct? Okay? Yep. Okay? So if you refer to so applying KVL, just using this similar approach here, you notice that if we represent all the values as an unknown here, okay? So it's essentially, so what you have here, you have a KVL around here, right? Around loop 1, okay? So what I can do is I want to find the current, solve for I, right? So by applying KVL, we have negative V equals to V1 plus V2, okay? Equals to, oops, sorry, V equals to, this is equals to 0 for starters, sorry. So V equals to V1 plus V2. Applying Ohm's law, V equals to I, R1 plus R2, right? Right? So that's how we get to this relationship here. Okay? Just do a division. V divided by R1 plus R2 to get I. So now if you want to find the voltage across each resistor, you can do V1 equals to I times R1. So substitute I here. You substitute I. So you have an R1 here. This is your substitution here, right? Okay. Same goes for V2. You have your R2. Your I is essentially this one. Right? So what you notice is that you can actually write this relationship as follows if your number of resistors increase, which is shown here. Right? Essentially your resistance of interest divided by the total equivalent resistance multiplied by the source voltage. Okay? So it gives you the voltage across the resistor itself. Okay? Right? So in the last 10 minutes, I'll just go through the questions once again. Just do an example of voltage division here. Oops. Okay, just do it on paper. So this one here, we have a 12 volts, 2 resistors in series, right? 18 kilo ohm, 1.2 kilo ohms. Okay? So method one is actually the KVL way. Method 1 is KVL. Okay? What we can do, apply KVL across the loop, right? So I label this V1, I'll label this V. So today I want to see what V is. So what is V? Right? So what I can do, applying KVL I have, across loop 1 I have, negative 12 plus V1 plus V equals to 0. Okay? Then, just give me 1 sec. V1 plus V equals to 12 for now. Okay? Okay? So now I also know that I also can write, I apply Ohm's law here. Okay, apply Ohm's law. I need to label my I as well. I have I multiplied by my 18 kilo ohm plus I multiplied by my 1.2 kilo ohm equals to 12, right? So this allows me to find I, which is equals to 0.625 milliamperes. Okay? So at the end of the day, we just want V, which is equals to I multiplied by the 1.2 kilo ohm resistor, which essentially gives us 0.75 volts. Right? So this is the long method way. Slightly longer method. The idea is that you need to find I first before you can find the voltage of interest. Okay? So for simple questions like this, you can use method 2, which is the voltage divider method. Yeah. Voltage divider. Okay, very easy. V is essentially the voltage source, 12. Write this out. Voltage source multiplied by the resistor of interest over your R equivalent, right? So voltage source is equals to 12. The resistor of interest is 1.2 kilo ohms. Total is 18 plus 1.2. This gives us, once again, just 0.75 volts. Okay? Although you notice that this step might be a lot more faster compared to what we have here, but you need to know that you're actually remembering an additional formula here, and sometimes circuits are actually not so simple that you can just use the voltage divider or the current divider rule right away. Okay? Okay? So I think, yeah, that's it. So last thing, before you go, a summary. A summary of what you have learned over the past 2 weeks, okay? So in week 1, you learned about, so right now, up to week 2, you already have 3 tools that allows you to solve circuit questions, okay? First one, Ohm's law, which is V equals to IR. Remember, once again, every electrical component has their own V, I, and R. Okay, so when you label them, you can label all 3 of them. It's still correct. Okay. The next 2 tools, you have your KCL and your KVL. Okay, so KCL states that the sum of currents, right? Remember Kirchhoff's current law. We are referring to currents here. At a node is equals to 0. Okay. Kirchhoff's voltage law, the sum of voltages in a loop is equals to 0. Okay? Notice that the similarity and the differences. Current law means we are talking about currents. Voltage law means we are talking about voltages. And for KCL, we are looking at nodes. For KVL, we are looking at loops. Right? So applying KCL to parallel resistors, we have this R equivalent calculation. Applying KVL to series resistors, we have this R equivalence instead. Okay? And from here, we have the current division rule and the voltage division rule. Okay? So my advice to you is that, although these are really simple, I would say, although this helps to simplify your calculations by a lot, but you need to take note that for more complex questions, it is usually advised to just go with KCL and KVL right away. Okay? All right? Okay. So I guess it, yeah, question? Yep. If you have multiple sources, is it? It depends. So if you have multiple sources, if you have a simple circuit like what I mentioned in the slides just now, okay? If you can see it directly like this, then you can sum them up. Perfect. However, most of the time, I think it will be a lot more complex than this. You have something like this, then maybe you might have, an example is that you maybe might have something like this as well. Maybe another voltage source here. Oops. So it makes everything so confusing. And you need to just use KVL or KCL right away. Okay? Instead of summing them up. Alright? Okay. Alright, so that's it for now, for today. And see you next week.
There's a